Welcome to TeleGeography Explains the Internet, the show that explores the business behind all of the ways humans stay connected around the world. I'm your host, Greg Bryan, and today we are continuing with our 5-part series explaining exactly how data actually moves around the world. If you didn't listen to the first episode in the series, go back and check it out. It's called What is the Internet? As each episode builds on the previous one. So today we're on number 2. What is the transport network? So one of the most important lessons from this entire series, I think, is that the vast majority of data is transmitted over physical wires, not over the air via spectrum. A lot of people unfamiliar with telecoms are really surprised by that fact. But for a lot of internet traffic, the only part of the journey that is not actually on physical wires is from your device to your Wi-Fi router. So often when I explain the transport network, I like to bring up Spaceship Earth at Epcot. If you're not familiar, Epcot is a theme park at Disney World in Orlando, known by its big silver ball at the front of the park. Well, there's actually a ride inside that ball, and it happens to be all about telecommunications, as the ride was originally sponsored by Bell Telephone and later AT&T. So there's actually a scene in the ride where these women in 19th century dresses are sitting at a switchboard in what was then a central office, which we'll learn about later, and they're literally connecting cables from one port to another. So in the original telephone system, you would connect to your local switchboard. A person would answer the phone and ask where you wanted your call directed, say Pennsylvania 65000. Then they would plug you into that circuit. And although an incredible amount has changed, this is still useful to understand the fundamental foundation of how the internet works. Back then, you were literally connecting a circuit between two speakers to carry your voice as a signal, whereas now service providers are breaking traffic up into packets of data that are switched via routers. Those packets need a clear path between the original device and receiving device. And the wires, and sometimes a little spectrum, which we'll talk about, but the wires that help complete that virtual circuit are called the transport network. So first, we're going to be answering the question, what are the physical media of the transport network? First, we're going to talk about wires. As I mentioned, the vast majority of the transport network is made up of physical wires. There are wires laid all around the world, and they really only come in a few forms, which are on copper or fiber. So if you're old enough to have had real wired phones in your house, you might remember a twisted pair, a telephone wire, of copper wire. So while service providers have been phasing twisted pairs out, there are still millions and millions of miles of it carrying traffic all around the world. If you happen to access the internet through DSL, it's actually over this kind of wire. Because these wires were designed long ago for voice transmission, they are only able to carry smaller amounts of data, generally maxing out at fewer than 100 megabits per second. Often DSL plans are much less than that. So next comes along coaxial cable. When the internet first emerged, cable companies that had already pulled wires to homes and businesses for TV service realized they could send data over those same wires. This became possible in the late 1990s using a technology called DOCSIS, which has developed over the years to support bandwidths up to 10 gigabits per second. So a lot more capacity available over coaxial cable or DOCSIS than you have over DSL. Finally, most of the transport network is made of fiber optic cables. These are flexible glass or plastic fibers that transmit light over distance. And although they have some physical limitations, these fiber wires can accommodate massive amounts of bandwidth compared to copper wires. And there's a variety of methods to transmit data over wires. So for that, I'm going to invite my colleague Paul Brodsky to explain a few of them. Hey, Paul, welcome back to the show.
Thanks, Greg.
All right, so Paul, I've been explaining the transport layer and got to fiber optic cables, and I thought there's a lot of various ways that we can send data signals over fiber optic cables that I felt not up to the task of explaining. So let's start with maybe what we call legacy layer one technologies, which again, I'm not sure that's right, but that's why you're here, right? But TDM, Sonnet SDH.
Yeah.
What are they? We'll start with just basics. Like what do those names stand for? A lot of people have probably in the industry heard people refer to TDM or Sonnet and not even really know what they mean. And then secondly, how do they actually send a packet of data from point A to point B?
Is that all?
Yeah.
Thanks, Greg. I find it useful to sort of interweave, if you will, some, I guess, industry and technological history into all this. It's hard to kind of understand.
I agree. Yeah.
It helps to understand where we are now. It helps to kind of understand where we were, but to kind of get a sense of where we are now. So, I like to bore people around the office with, this notion that for a long time, telecommunications really meant like transport of the human voice more than anything. You could always mail somebody a letter. You could send a telegram over a telegraph line. Is that right?
Yeah.
Smoke signals, whatever you want to do. But the first, electrical telecommunications devices were really designed for people to talk to each other.
Right.
And just the way you and I are talking to each other right now. And those were by necessity analog designs, right? Mm-hmm. Because we are organic beings, right? I mean, we evolved over millions and millions of years our bodies have evolved over millions and millions of years to emit sounds and to hear those sounds. And so, because we live on Earth with an atmosphere of comprised of a gas that we call air. And so, in our bodies, we have lungs that express air and we have, larynxes and vocal cords that vibrate. We have, we have a tongue and a palate and cheeks and all this stuff and jaws and teeth that, I say teeth twice, that generate waves. They generate longitudinal waves through the air that are then
vibrating our eardrums.
Absolutely, yeah.
So what you're getting to is the soup can with the string between it, right?
Yeah, that's it, right?
Yeah.
And these are, and again, our what we recognize as language is, ultimately it's just pressure waves through the air.
Right.
And what you're hearing is your eardrum is vibrating, and your brain is smart enough to sort of process those, those waves and convert them into some sort of sensical information.
Right.
And that's the way, being animals have communicate for, whatever, millions of years or so. The trick was, we could talk to each other. I don't know, Greg, how good you're hearing, right? 10 feet away, 20 feet away. But how do you...
There's the tele part.
Yeah, that's right, exactly. Yes, yeah. Tele, Greek for distance, I think.
Yeah.
So, how, when Alexander Graham Bell invented, so to speak, the telephone, we were able to extend that voice communication over
very long
distances, right? Yeah, which was great. And so, the original telecommunications networks were designed to enable people to talk to each other through electrical circuits, right? So if you put this in the form of like a telephone, well, what is it? It's it's a device that you pick up, and it's got on the microphone, it's got a diaphragm that vibrates with your voice, and it generates an electrical signal that gets sent over wires that are where there's a voltage over those wires, so it could be picked up and repeated by a speaker tens of feet, miles, whatever away.
Well, this is my, woman in the Victorian dress with the patch cords in the central office.
That's right.
Yeah.
And so the Bell, the U.S. anyway, the Bell system, they built this nationwide. I'm vastly oversimplifying here, but it built this nationwide telecommunications system where people could talk to each other. At some point, though, it became so popular and so many people wanted to talk to each other simultaneously that the switching technology internally just got a bit complicated, and technology improved to the point where they were the engineers in the phone company were able to digitize those analog voice signals.
That is the key to the birth of the internet. Even though this is just for voice traffic, right?
And so the Bell, so it was the Bell Labs or Western Electric, it was a long time ago, developed in the early 1960s, I think, this system called the T system.
T carrier.
T carrier system. Thank you. Where they created a standard by which the human voice would be converted from an analog signal to a digital signal. And it's based on the actual physical characteristics of the human voice, the bandwidth, sort of the oral AURAL bandwidth of the human voice, which is measured between, I think, like 30 and 3,300 cycles per second, I think, hertz, I think. And so they decide, well, let's allocate 4,000 hertz of bandwidth for the human voice, and we're going to sample that human voice a certain number of times every second, and with every sample, we're going to assign it a certain number of zeros and ones. So you cram all those together, and you get at 8 bits sampled 8,000 times a second, you get 64,000 bits per second. That's to say 64,000 ones or zeros, and whatever combination.
Which should be ringing a bell to anyone who's been in the telecom industry a long time now. 64 kilobits per second.
Right. 64 kilobits per second is called a DS0, and it is, I suppose, a standard ultimately of human voice.
Digital signal, right?
Digital signal, DS0. So that's great. Okay, so now we have a stream of ones and zeros flying around at 64,000 bits per second. Wouldn't it be great if we could combine multiple DS0s into one signal? And in the US, that's the standard was agreed to, where 24 such DS0s would be combined into what's called a T1, which is the lowest level of the T system
so
hierarchy.
For those furiously doing math, 64 times, what did you say, 24?
It's
1.5 something.
Yeah, it's 1.3 something, and they actually, just to make things more confusing, they throw in another 8,000 bits per second for like framing and stuff. So you come up with this standard of 1.544. Yes,
that's and it's in Europe and elsewhere it's 2048.
Megabits per second. Yeah, they have their own. They did it slightly differently. And so that worked fine to combine 24 voice streams together. That allows for higher volumes of simultaneous calls. But it keeps growing, and technology keeps evolving. And in the early to mid 80s, we went from the electrical technology of the T1, the T system, to an optical technology where you're actually you're not using electrical impulses, you're using light.
Flashes of light.
That's right. Through, and what better medium to send light? You want to send it through air? Okay, but it disperses, and there's reasons why air doesn't work real great. What if you send it through glass, through long strands of glass? Wouldn't that be crazy? Turns out glass is a really good medium for this sort of thing, but only at certain wavelengths of light. This was the SONET standard was driven in large part by the breakup of AT&T.
Interesting.
Because suddenly you had all these local exchange carriers that had an option for their long distance. Right. They didn't have to go with AT&T. They could go with MCI.
MCI, who was the fiber optic commercials.
Or Sprint. And these long distance carriers couldn't, if they all just sort of came up with their own fiber technology, it would drive the local exchange carriers crazy. They'd have to have their own equipment, their own everything for every. So a standard was finally agreed upon. It took quite a bit of doing, whereupon the first optical standards, I assume it's the first ones. I don't know. There might be some that the ones that we know today, optical standards known as in the U.S. as SONET, which is synchronous optical networking, was agreed to. And again, what is that? It's just a matter of being able to further sort of interleave multiple T1s, T3s, or higher onto a single optical channel.
Mm.
And the base level of the SONET is actually something called an STS1, which is like 50 something megabits per second. But really what we talk about are STM1s, otherwise known as OC3, which is about 155 megabits per second. And that is really considered sort of the base level.
The baseline, so the right, the core, yeah.
In the US, it's referred to as SONET. In the rest of the world, they refer to it as SDH, synchronous digital hierarchy. It's essentially the same thing.
And just what this is actually doing is it's organizing how flashes of light can go down the same fiber optic channel simultaneously,
basically,
right?
Yeah,
so that you can have multiple channels going on this same fiber optic cable.
You can have multiple voice channels over the same fiber optic cable. Yeah, that's right.
Right.
It's interesting. SONET and SDH it's optical, but it's by today's standards, I think it's pretty rudimentary in that the keying, so to speak, is exclusively what they call on-off keying. It's like a flashlight that you turn on. It's like Morse code.
Mm-hmm.
It's either on or it's off.
Right.
And at ridiculously high rates of speed.
But that works well with ones and zeros.
Yeah, that's right.
Yeah.
But there have been advances in optical technology that allow you to play games with like phasing and polarization, all that crazy stuff.
And that's how you get more bits across the same strand of
fiber.
Oh
yeah, a lot more. But SONET is it's an optical networking technology, and it is allowed for just immense increases in throughput through physical medium. I mean, there are further advances in optical technology. I mean, I don't want to stop at SONET because it would kind of give you the sense that the world ended. The technology advancements ended in the late 1980s. I mean, nothing would be further from the truth, right?
So what came after?
Yeah, what they call wideband division multiplexing, and then
yes.
dense wavelength division multiplexing, which allowed you to put multiple optical channels, that is to say, multiple optical wavelengths running through the same strand of fiber. Mm-hmm. You could have dozens of different wavelengths on the same. Similar to the way that if you turn on your radio, just depending on how you tune your radio receiver, you can receive anything from 88.1 megahertz up to 107.9 megahertz just on your FM dial.
So it's kind of like spectrum within that
Absolutely.
Strand of fiber.
Oh yeah,
okay,
yep, that's exactly right.
Interesting.
And it gets even better because more recent improvements in technology, what they refer to as coherent technology, allows you to play games essentially with certain really cool characteristics of light. The polarization of light, you could have at the same channel, you could have some pulses of light, say vertically polarized and others horizontally polarized, and the detectors and the intelligence can distinguish between those. So you're able to distinguish between different types of symbols. There's also phase changing, right? So we're using laser light, which by definition is in phase.
That means like together, basically, right?
In phase, and you can actually, and you can designate like a base phase, and if you just and you can manipulate the phasing. You can back off by a quarter of a wavelength,
so that
or
there's
half a
a
wavelength,
slightly different signal.
That's exactly right. So so just the and there are other things. There's amplitude modulation. There's all sorts of really cool things you can do with laser light to cram ever more ones and zeros through a strand of fiber about the width of your hair.
That what you're talking about is DWDM, which is pretty much the currency of the realm now in terms of sending data across long distances.
Yeah,
right?
And not just DWDM, but coherent DWDM.
Coherent.
Yeah, that's where we are now.
Would you believe that that's the first time I've ever heard that phrase? Yeah, so I
have been doing my job.
Yeah, I love it when I learn something new like that. That's fascinating. With DWDM, we've often thought, maybe this is a little philosophical, but everyone understands that that computing technology, we have this thing called Moore's law, and you can build smaller and smaller transistors, but it's a totally different concept, but has kind of maybe kept a pace with Moore's law, that we can squeeze more data out of the existing same strand of fiber, basically.
Yeah,
right?
We're approaching something. I keep saying Nyquist. It's the corollary to the Nyquist equation, which is the Shannon limit.
The Shannon limit. I've heard of that. I don't understand exactly, but
it basically says that it's a law of, I guess, information theory, which is really just based on physics, which is, if you define a certain communications channel by a certain signal to noise ratio and a certain amount of bandwidth, there's just a physical limit to how much information you can jam down there.
Right.
And we're kind of approaching it now.
Much like we have approached that with transistors, unless you get to the quantum computing level and all that sort of, right. Yeah.
So, how are and in particular, this is a particularly acute problem in the submarine cable business, where the cost to lay a submarine cable is really, really high. So you can't just lay cables willy-nilly. You really need to squeeze every last bit out of a cable. And so some of the improvements that the industry is seeing are they're remarkable, but they're not. It's not like it's whiz bangery. It's like, hey, we need more electrical power to the optical to the amplifiers.
Even different sorts of advancements, like we can do this without using as much power, or that sort of thing. Yeah.
But here, because we're on the actual strand of fiber, we're kind of approaching the Shannon limit. One way to get around that is to, instead of running just two pairs of fibers through a long haul cable, or four, which was the case 20 years ago. Let's jam 24 down there, and and that certainly increases your throughput on the cable as a whole. Problem is, you got to power those things. You have to power the amplifiers. You need amplifiers every 50 miles or so under the ocean just to keep the optical signal running. And one of the challenges has always been, how do we get all this power down there? And so, there are advancements that there's been some. One way to approach this is to actually replace the electrical conductor. It's typically been copper. Aluminum actually can work a little bit better.
I did not know that.
So there's a couple of cables. There's one in the Pacific and one in the Mediterranean that's actually been laid with aluminum power conductor.
So you happen to be an expert in metallurgy. Isn't aluminum brittle?
I know, right? And I think that's why there was a push at some point in the wasn't there, to aluminum wiring in houses that had a tendency to catch fire, though.
Right. Exactly.
I think the problem was that I think the problem, I'm getting way off we're getting way off base here, but I think the issue was where copper and aluminum met, I think.
Excellent. All right, so that's layer one.
There's
6 more to go, but luckily we're only talking about 2 of them.
Let's talk session layer, shall we?
Yeah. So for long haul transport, most of it's happening over layer 1, but of the last decade or so, a lot has been talked about at layer 2, which is not exactly the same thing, but often referred to as carrier Ethernet. Right. So what is carrier Ethernet when we're talking about long haul transport as a switch network? Why is that different than layer 1, and why was that useful for carriers to develop?
So Ethernet was developed as a local area networking technology, right?
So everyone at home listening to this, who's old enough at least, had a Cat 5 or Cat 6 cable plugged into their machine that was going to their modem. That is an Ethernet cable, and that is a layer 2 transmission technology. Yeah. This is just layer 2 over a wide area network instead of a local area network.
Yeah. So I don't know, somebody came up with a bright idea a while ago that, wait a minute, Ethernet works so well as a networking technology in an office, in an office campus. Ethernet switches have gotten really, really cheap.
Right.
Their transmission speeds, they started out at, just Ethernet was 10 megabits per second. And then there was fast Ethernet, right? That was 100.
Yeah, FastE, and then
Giggy. Which is 1 gig per, and that's 10 gig Ethernet.
That is one nice thing about Ethernet compared to optical transport is the math is really easy.
Yeah, right.
So,
that's a really good point.
We evolved with 10 fingers.
That's
not
right.
12.
It's base right. We're talking base 10 here.
Yeah.
About time. So there's a lot of that equipment out there. How many Ethernet equipment vendors are there, Greg? Right.
Right, absolutely.
It's
Yeah.
a million.
Yeah. Whereas this optical stuff is very specialized.
Yeah.
So, yeah.
And I mean, let's face it. Like the data that's so much of the data that's flying around is like connecting up computers, right?
Mhm.
Ultimately,
Right.
So
that
why
are
not?
Already there, all the LANs that need to be connected to each other over distances are all already on layer 2
Yeah.
anyway. So you had to translate that layer 2 to the layer 1.
Yeah, you're just
Yeah.
running it over say Sonnet,
Mhm.
right? I mean, Sonnet is transporting data. Doesn't
Right.
really matter what kind of data. It's optimized for voice, but there's no reason why you couldn't run.
Right.
Any kind of
Hence
data
why
over that.
like this first came into my world as like Ethernet over Sonnet, right? Whereas now there's native Ethernet, meaning just sending Ethernet over these long
Right.
stretches themselves, right?
Right.
So, yeah.
Yeah. So you're basically think of it as like pointing these Ethernet ports instead of having them, sort of face inside the office, turn them around 180 degrees, and
Right.
have them face the ocean. You know what I mean? And
Yeah.
talk to another Ethernet port, 1,000 miles away.
That makes
And
sense.
it's very important. We get to like layer 3.
Mhm.
We talk about packets and routers. Those routers, they all have layer 2 Ethernet ports on them
Right.
that you literally plug.
So they're already ready to be multi-protocol.
Yeah, that's right.
Yeah.
So, yeah.
Excellent. Interesting. All right. Now, Paul, the last thing I want to talk about, since we've covered the sort of basics of how we transport data over these wires, and as I've explained, it's mostly wires. But the average person thinks of the internet as something that just happens magically in the air. there is one segment of the journey that it does, right? So from my device to a cell tower, briefly, what is happening?
Right. So it's funny, like you and I are in this world where we talk about fiber and infrastructure all the time.
Right.
But let's face it, we always carry around this this phone in our back pockets all day,
and it's
right?
always connected.
It's always connected, right? There's this idea that what do we call it? It's a wireless device, or it's a mobile phone, or if you're a little bit older, you would refer to it as a cellular phone.
Right.
The only part of it that's like untethered, like that is connected by radio, is just from you to the nearest cell site, and referred to as cells because if you think of a map, right? If you just imagine in your head a map of whatever, a city or a town, wherever you are, there are referred to as base transceiver stations, located periodically on top of office buildings, or on towers, or on maybe an old radio tower,
a little
or
pole with white rectangles.
Right. You see them all. If you're not looking for them, you won't see them.
Right.
But if you start notice one of these things, right? If you start looking for them, you see them everywhere, right?
Some are even disguised as trees.
Some of them are even poorly disguised as trees. Yes. Yeah. I mean, so your phone, in its most basic form, is really like, I hate to say it, I'm going to get yelled at for saying this, but it's like a walkie-talkie, right? It's got batteries.
It's using radio frequency.
Yeah,
right?
It's got a battery in it. It's got an antenna.
Right.
It's got a transmitter, and it's got a receiver, and a whole lot of intelligence. Right, probably more intelligence in my little iPhone than Apollo 11 had on the way to on its way to the moon.
It's not even comparable. Actually.
Yeah, right. It's bonkers. Right?
Yeah.
Sometimes I like to shoot this thing to the moon. So imagine. Your phone is in radio communication with the nearest cell tower, and that radio communication it's over some radio frequency spectrum, which is licensed by the Federal Communications Commission at whatever 1900 megahertz or 800 megahertz or 900.
And that refers to the wavelengths that particular radio frequency is using.
The wavelength and frequency are inversely proportional. So the longer the wavelength, the lower the frequency.
Right.
That's really all it is. Now, what we don't really see are all that whole network of cell towers I described. Those, in fact, have to be effectively hardwired for the most part.
They have fiber optic cables that are running probably DWDM right now.
Now,
right?
when I was doing it, I was a radio frequency engineer years ago. We would run a T1.
A T1.
Every site.
Yes.
I'm dating myself. I'll explain some of the some of the nonsense I'm spouting. But back then it was a T1. But then what were the phones for? They were for talking to people.
Right.
That's it.
It was voice channels, 24, 64 kilobits.
You might be able to send some rudimentary text, but that was about it. So as the quantity of data flying between your phone and the nearest cell site, has increased exponentially, the bandwidth to those cell sites needs to expand as well. And that's, as you're saying, Greg, now it's fiber to the cell site.
Okay, so we've all heard about these changes in the way that we send mobile signals, 3G, 4G, 5G. But the upshot for us listening now is it that basically you can send more data because our mobile devices got way more data intensive than they had been.
Yeah. I mean, it's sort of a virtuous cycle with apps, right?
Right.
I mean, the more access bandwidth that the end user has, and the more processing power the phone has, then the more sophisticated apps we can use, right? And it just sort of grows on that.
And that for the purposes of what I'm after in this episode, really, that it's the transport network. How do we get data from point A to point B? That most of that is still happening on wires, buried in the ground or hanging from the telephone pole. Yeah. And so there's really just this short journey from your device to the closest cell tower. Yeah. And then from there, it's all wires all the way until it reaches the other end where maybe someone's on a mobile device.
Yeah. I mean, there's only, unlike cables, meaning fiber optic cables, where the signals are, contained within the fiber, radio spectrum, like that, that connects your phone to the cell tower is, there really is a finite resource, right? Your carrier only has access or is only licensed to operate at a certain spectrum. So they have to be very careful about how they reuse their spectrum throughout their network. So what you'll find is that as more and more customers come on the network, or as more and more spectrum is needed for each customer because of more intensive, that the carriers need to continually build out and make more densify. Make more dense. Their cell phone networks. So because they only have access to so much spectrum, so they have to reuse their spectrum, and they have to be careful not that one cell site does not interfere with another one. So they tend to build the sites, particularly like in the cities, in the city cores, they tend to build them at lower heights. And they tend to sort of down tilt antennas, so the optical, the radio signal doesn't, doesn't splatter all over the place. Yeah.
Interesting. Yeah. Okay. So that's a great point. So that ultimately the big advantage that wires have over radio frequency is that you can put as many wires between point A and point B as you want, whereas radio frequency is a limited resource. In fact, you have a map, don't you, from the NTIA of all of the spectrum? And correct me if I'm wrong, but in I'm sure this is true in most other countries too, but the Department of Defense has access to the best spectrum, if you will, and then terrestrial television after that, right? So the mobile providers are probably dealing with not the oceanfront property, so to speak.
Well, it depends on the application, right? So, like what I was saying before was, in a cellular, in a mobile phone network, you don't want spectrum. You don't want radio spectrum that has, say, too short of a that decays over too short a distance, right? At very high frequencies, the signal goes a very short distance and then it just drops off. Conversely, at very low frequencies, it can go for miles and miles and miles and miles. You don't want that if you're a phone network. First of all, at very low frequencies, you just can't carry that much data. Right. And you would just be interfering with yourself constantly because the signal would carry for miles and
catch
miles
other
and miles.
signals.
So
you want a denser tower network and then pull wires to all those towers.
If you have a lot of customers there, right? You
Mhm.
don't want to waste money on building towers if there's only a few people there. That's why if you go out and in the countryside,
Right.
you may see these towers with
Very tall.
yeah. with these big panel antennas, maybe
Mhm.
hundreds of feet up in the air, because they can serve a very large geographic area without
Mhm.
fear that there's going to be sort of
Interference.
what they refer to as co-channel interference.
Right.
Yeah.
Right.
Whereas the opposite is true in a dense inner city. You want those sites low. You want the antennas down tilted, because you only want each cell to cover a very, very small parcel of land,
Mm-hmm.
because you don't want to serve too many people and overload your network, and you got to reuse that spectrum somewhere fairly close by. Yeah.
Right. Which again is why wires make sense whenever they're practical. Right?
Absolutely. Right.
Yeah.
So terrestrially, under seas, again, you might have the most recent, cable builds, long haul cable builds might have like 16 fiber pairs.
Mm-hmm.
I've heard of like 24 maybe on one of them. But even there, you could use the same optical wavelength, so long in different fibers.
Right.
Because they're not going to interfere with each other.
Yeah.
They're enclosed. Those signals are enclosed.
Mm-hmm. Whereas
Terrestrially,
you couldn't do that in spectrum. Right.
Yeah, you couldn't do that. Terrestrially, you might get 128 fiber pairs down one conduit,
effectively,
or more.
Infinite.
Yeah.
Sense.
So spectrum, even optical spectrum, is not really as much of a concern terrestrially.
Excellent. Well, Paul, that was very helpful. Thank you so much. I'm sure that I understood about 80% of what you said. So
it's about as much as I understood.
All right. Thanks.
All right, Greg. Until next time.
So before we get into the various segments of the transport network, I also want to address satellites. And for that, I have brought on resident telegeography satellite expert, Peter Wood. Welcome, Peter.
Glad to be back.
Yeah, exactly. So, first you've been on to talk about Latin American telecoms. We did a whole episode together all about satellites. That was episode 404. If you want to go back and listen to that, we go into much more detail. But I just wanted to nail down some basics as they fit into the overall picture of what the transport network is today. So first, Peter, how much of the global transport network goes over satellite connectivity?
Well, it's not the most exact science of measuring it for a lot of reasons, but the general consensus seems to be like 1% or less.
1% or less.
It's very small.
That is the key. That's the takeaway from this segment, I think, right, is that 99% of traffic on the transport network is on wires.
In that general range, it's something that is, in general, not particularly central to how telecommunications functions. Mm-hmm. But when it is important, it's very important because it's often a last resort or the only physical way to get connectivity to happen.
Yeah, because certainly before I was in the telecom industry, I would have thought a whole lot of it was on satellites.
You're not alone.
Yeah, absolutely. All right, so let's do a quick review. This is something we talked about a lot on that episode, but just a quick review of the general orbits that satellites can take for communications.
So for the longest time, the main orbit is called geo orbit. It's often called a few different things, but basically satellites that are very far away from Earth, something like 22,000 plus miles away, very far. Advantages is that just the geometry of it, you can pretty much see most of the surface of the Earth on that side of the planet. So you don't need a lot of satellites, sometimes as few as one, to be able to do the job that you're trying to get done, whether it's observation or communications. A lot of different types of satellites were that far away and to this day are in that orbit. Mm-hmm. We're seeing a lot of investment in something called LEO, which is low Earth orbit, that's significantly closer to the Earth, something like a tenth of the distance or less compared to GEO, depending on where exactly you are. There's variation within each orbit as well. Of course, yeah. And then there's also MEO, which is kind of in between those. So it's roughly broken up into those three categories. There's also some that kind of go into different orbits or pattern of orbits, and not so much about the distance as much as it is how it's circulating the Earth.
Polar instead of equatorial.
Yeah, exactly. So HEO is one of those. But the basic idea is distance seems to be the most important because with LEO, where there's a lot of investment, like we're saying with geo, you can see a lot. LEO, because of the geometry, you see a lot less of the surface of the Earth, so you need a lot more satellites.
Right.
And they need to communicate with each other pretty quickly and efficiently, and also
Skynet.
ideally not collide with each other or
Right.
other companies' satellites. So there are advantages and disadvantages to every orbit, but they're mostly broken up into those categories.
LEO, GEO, and MEO. Gotcha. All right. And so the other question that I really wanted to ask you, and again, this is from a high level perspective. We're not going to get into any kind of engineering or anything like that, but just as a general concept, how do satellites actually send data over the air to someone on the ground with a receiver?
For the most part, it's through radio frequency. So there's different bandwidths that you're sending waves of sound, but it's got to get transmitted or converted into something that can go onto submarine cables, for example.
Right.
So
ones and zeros.
Exactly.
Yeah.
So we see that there are teleports. Basically, you need to be able to connect the Earth to the satellite somehow. So we have devices that will connect. And then in the LEO, for example, there will be, so we're seeing a development in this, optical communication. So visible light, like laser type communication.
That's in space, though.
Communicating between different satellites just to make that a more efficient network. So instead of having to bounce back and forth to get around the globe, you can bounce up, lateral move to a different satellite in the constellation, but down to a different teleport.
So my packet has an address that it needs to get roughly from this continent to another. It goes up to the satellite, then by optical laser across to the other satellite that's over that continent, and then down to a receiver.
That's one option. And there's a lot of engineering to it that's really complicated. And it gets further complicated because there's a lot more integration of companies, both within companies and mergers and acquisitions and partnerships between companies that have satellites in different orbits. So we're seeing that there's more and more pressure to have the satellites communicate between LEO and MEO and GEO, or some combination thereof. So there's a lot of ways to do it. The short answer is, the laws of physics, that we can communicate with different waves. Some of it's on the spectrum of light. Some of it is more on the other part of where it's not visible light.
Right.
But it's happening, usually at a microscopic level, and it's happening between Earth and space, and also between satellites within space, and also different mixes of how that's composed.
And the upshot is that we have this sort of map of spectrum, if you will, and there are parts of that spectrum that are carved out for certain uses, like radio, broadcast television, and one of those sections is reserved by everyone for satellites, basically.
Yes and no. So it gets complicated because there's every country has its own regulatory bodies. So every country can carve that space out differently.
Right.
So that's a lot of lawyers that a lot of companies need in order to get the rights to be able to transmit on those frequencies. But the general principle is that different frequencies or different parts of the spectrum are better suited for different types of communications. So something like Morse code to a shipping vessel is not going to need nearly as much bandwidth as being able to, for instance, stream this podcast episode.
Right.
So that, especially lately with the KU and KA bands and C bands, there's different bands where it's better adept for things like audio and video communications, which means that it's a lot more intense, that the frequency is a lot higher, the waves are a lot different size compared to the ones that don't need to carry as much information packed into it. The difficulty with that is the interference from things like storms or clouds or whatever makes it a lot harder to really direct that. Like I was saying earlier, there's a lot of complex engineering that gets into it, and I don't know all of it, but I know enough to know that it gets complicated in the ability to balance those needs and restraints is tricky, because we can't do a lot about clouds, for example.
Well, if you knew more about it, it would go over my head, let alone everyone listening to this anyway. But that's great. Yeah. And so certainly, in the wired world, we have hazards like storms that can knock down poles, or shovels that can dig into wires, or anchors that can drag along. So none of this is without its calamity.
Risks,
right? Yeah, exactly. Excellent. Well, that is really useful and helpful. Thank you so much for joining me, Peter.
Glad to contribute.
Cool. All right. Great. Thank you so much, Paul and Peter. Now we're going to talk about segments of the transport network. In the journey of any data packet, there are going to be different segments with different characteristics in terms of the geography covered, the underlying infrastructure, how the network operates at those levels, and how much it costs to use the wires at that segment. And there are many ways one could slice this up, but I am going to divide the transport network into 5 parts: the local access network, the middle mile network, terrestrial long haul, submarine cables, and finally wireless, which covers mobile and satellites. Telecoms works like many other networks, natural or human ones, that you might be more familiar with. On the nature side, you could think of streams, maybe that start as a trickle, perhaps from snowmelt or a spring, and feed into bigger and bigger creeks and waterways until they meet a huge river and flow into the ocean. That's essentially, in a way, how data flows, but I think human design systems are often more apt for analogies, and for that I really like to use the airplane model. So for this, let's say that you live in rural Vermont and want to visit family in their village in rural Norway. You might drive alone down a gravel road leading to your house to get to a larger road and then eventually a state highway. Finally, you get to the interstate highway, the largest and most developed road, and you take that to the Burlington, Vermont airport. There, you get on a small plane from a regional carrier with propellers that seat only maybe a couple of dozen people. And you fly to Logan International Airport in Boston. You board a much larger plane with hundreds of people, all bound for Heathrow Airport in London. Now, this transoceanic flight carries the most people and cargo and is on a major carrier. At Heathrow, you board yet another small plane that is again operated by a regional airline and bound this time for Oslo. Once you get to Oslo, you board a regional train that takes you a couple of hours to a small city near your relatives, and there they are waiting for you to drive back to their rural house, reversing those development levels of the road from national highway down to gravel road. This is at bottom quite similar to the journey your data packets need to take. If you instead email your Norwegian cousins a video, first the packets travel down the wires going to your house. This is what we call the local access network. Local access networks take traffic from individual homes, businesses, and even large corporate or educational campuses to a carrier's point of presence, or POP as we call it in the industry. The first aggregation point of those local wires is usually something we call a central office, at least in the US. Name might vary around the world, but the same concept. I want you to actually look around your neighborhood or your town, and chances are pretty good that you can find a small windowless building with the logo of your local telecommunications provider somewhere nearby. Here's where they aggregate all of the data lines from eyeballs, as the folks in the industry often call individual customers. This is like the point where you may leave the gravel roads and small streets to get onto the slightly larger state highway in our travel example. And this is often actually the most expensive part of the journey, at least on a per bit basis or a unit cost. It is costly to dig trenches or hang wires on poles to get to actual end customers, especially when those customers are rural or more remote from larger telecom infrastructure. So that can be the most expensive part of the journey, getting to that actual endpoint or customer premises, as they often say in the industry. Now, once your data packets get to the central office where your carrier or internet service provider aggregates all of the local traffic, it has to get to the larger backbone network. From our travel example, this might be the smaller state highway taking you to the large 4+ lane interstate highway. Now, this part of the journey is called the middle mile. Your ISP may already be handing your traffic off to another provider at this point, or they may own the wires all the way to the destination of this leg of the journey, which is the Internet Exchange Point, or IXP. Your data then gets to an IXP, which is often in a Tier 1 or at least Tier 2 size city in your country. As in our travel example, the terrestrial long haul is the major interstate route, say I-95 between major cities. So our data that is going to cross the ocean eventually would likely go from rural Vermont to an IXP in Boston, and then on to another carrier's terrestrial long-haul backbone to New York City. Or if your cousins were in Japan, say, instead of Norway, it would likely go all the way across the country to Seattle or some other submarine landing point on the West Coast. As you can imagine, the cost to send bits over the terrestrial backbone are some of the lowest costs in the whole global network. Providers that go through the hassle of digging trenches or laying fiber ducts across these large trunk routes are building massive superhighways, so the supply is huge compared to the earlier legs of the journey. Competition on these routes is also much more fierce, since everyone needs to be connecting these major IXP cities. Finally, if your traffic is destined for another continent, it is almost certainly going to travel over a submarine cable. These cables are laid across the seafloor to send bits across wires on our watery planet. This is our long-haul intercontinental flight in our travel example. And you will often find that the major transoceanic flights, as well as shipping channels, follow very similar routes as submarine cables. They connect to the big population and economic centers around the world. Now, people are often really fascinated by this leg of the journey, so I invited my colleague Lane Burdette to tell us a bit more about them. Welcome, Lane.
Hi, Greg. How you doing?
I'm doing great. Now, we've talked a lot about submarine cables, but we wanted to have you on here in this episode to just give us like the really high level important things that one must know about understanding the global transport network. So first, I've got a little trivia question for you, which is just roughly how many cables are there in the world? I know there's a lot, but I don't have the first clue what the actual number is.
So many. Okay, yeah. I looked it up today for you.
All right, good.
Hot off the presses, the number of cables that we show on our subcable map online, we have 506 that are in service, another 62 planned. So 568 total on the map.
Wow, that is a lot, especially considering like how long many of them are. There's a lot of
it's like millions of kilometers.
Yeah, millions of. That is really fascinating. So when people see our maps and stuff, there's this representation of the cables. But what do the actual cables look like? Like how big are they?
Yeah. Classic example: garden hose.
Really?
It's about that big around, yeah. Oh, it's
podcasting. That's okay. Yeah, we will have some video of this, so maybe that'll be a video moment. So about like a garden hose, which is definitely smaller than I think a lot of people think.
Yes, and it does vary some by how deep in the water you are. So when you're closer to shore, they need to be more better armored, better protected, and that's going to be a little bit thicker.
Because there's more dangers near the shore.
Yes.
Gotcha.
Yeah.
Okay. And since you mentioned that, so where do they land on the shore? So are you going to be walking along the beach sometime and just stumble across a submarine cable?
I wish. Oh, man. Maybe if you're in Porthcurno, like one of the old telegraph spots, find something that hasn't been pulled up yet.
Yeah.
But all the modern cables are buried.
Mm-hmm.
So unfortunately, my deep sea diving dreams about finding a subcable on the seafloor probably won't happen near shore.
So they're buried just like a certain distance out from the shore.
Yes.
In the actual like ocean, they're just laying on the seafloor, right?
Yes.
So, gotcha. Yeah. And then where do they go? So if we were going to try to find like where a cable lands, what are we looking for?
Probably wherever it's easiest to get a permit. Nice beaches are always good.
Yeah.
Somewhere worth visiting. But yeah, a cable is going to be laid bare on the seafloor and then be armored and eventually buried as it gets closer and closer to shore. Then the cable goes kind of under the beach or under that area, usually up to the beach manhole, which is kind of an access point.
Okay.
And
so
then,
that you can get down to work on it. Or
if you need to. That's going to be kind of near the water.
Right.
And then over to wherever the cable landing station is. And that's where it hits the next piece of like telco equipment.
Right. Then it gets pushed onto terrestrial networks and other segments that I'm talking about. So what does a cable landing station look like roughly?
could look like a lot of things.
Yeah.
It kind of depends, because you have some places where it just feels like a shack or something, you know,
Right,
like
they're
it's just
pretty small.
It can just be
nondescript,
there's some
yeah.
building. They're often manned. Somebody's in there, working the equipment or whatever.
Like a network operations center kind of thing.
That type of thing. Yeah.
Gotcha. Okay.
So, but sometimes they can be more like high security,
Mm-hmm.
fence around them, gate, stuff like that.
Well, they do kind of, control global communications and the whole economy. Right?
Sure,
Right? It's a little bit important.
There's a rationale for it.
Yeah. All right. So we talked with Paul, and I've been talking about in this episode kind of how you get data across wires and stuff. How much data can providers push across these cables? It's not infinite, right? But it is a lot, right?
So much.
Yeah.
So much. I was trying to find you a good example. Something that gets cited a lot is the Do Not cable, which is a Google system in the transatlantic. Transatlantic, by the way, is the biggest route.
Right. It has the most capacity, the most cables.
Biggest demand. So Do Not has like 12 fiber pairs.
Okay.
And using those, they have the potential capacity of 250 terabits per second.
Wow. Okay. Yeah. So we're usually talking about megabits or maybe gigabits, but 250 terabits per second. That's if everything's lit up, as they say, and under full utilization. But because when I talk to people who even sometimes are in the industry or not super familiar with telecoms, in general, anywhere in that spectrum, they are really surprised that you lay this thing down on the seafloor and there's only 12 fiber pairs in it, which is larger than it used to be, right?
Sure. Yeah. Transatlantics used to just be 3-4 fiber strands or whatever in there. And it's really bumped up recently as we need to get more and more capacity across these systems.
But it is that you can fit a lot of bits across fiber optic cables, right? So
absolutely incredible. Yeah. So like 250 terabits per second. That's the Library of Congress 3 times per second.
Wow. Okay, that's exactly the kind of soundbite I was looking for.
I got you.
Figure out what exactly that means.
It's huge.
Yeah,
it's huge.
Yeah, absolutely. All right. So the last question I have for you, Lane, is just how this works, and we don't need to get down to the sort of like engineering level, but just at bottom, there's these fiberglass, cables, right? So not fiberglass, fiber cables made out of glass, right? That are laying there. How do we actually send signals over them?
Yeah. So that's going to happen at the cable landing station primarily. That's where the signal first gets sent out. Right. Then, that's where the transmission equipment is stored.
Yeah.
Nice. If you're working on a really long system, like if you're going transcontinental,
like across the Pacific Ocean.
Those would be the longest. Yes. Definitely repeater those, but they have repeaters on them, and that helps re-amplify the signal as it goes across the ocean. So if you're just, in your head, imagine a laser or a beam of light shooting down all the way across the Atlantic, it might not get there. It's going to degrade
during the trip. Right.
So you have to boost that up as it goes along to get it to the other end and to connect to either maybe a continuation of the same telco provider's equipment or connect maybe to its next network provider.
Gotcha. So are there electrical cables going along this to power repeaters and stuff as well?
No, the repeaters themselves aren't connected to a second cable that powers them. Yeah. My understanding is that, the materials required for that are included in the cable itself.
Gotcha. Yeah. That is just really fascinating. So, thank you.
Some cables are cool,
Absolutely. Cool. All right. Thanks for joining me.
Absolutely. Have a good one.
All right. Okay, thanks very much to Lane for that explanation. Now we're finally going to talk about the wireless part, mobile and satellites. The final segment of the transport network is over spectrum, in our case, either as mobile service or satellites. Mobile service really belongs in the local access category in a sense. Of course, the big difference between mobile and wired service being that you can move while you're on a mobile device. But ultimately, your signal needs to find a nearby tower, which would be very nearby if you're on 5G, as the radius of 5G signals is smaller than previous versions. and then onto likely a fiber optic cable that is connected to the tower. There are mobile last mile connections to houses and offices called fixed wireless access. They're generally only used when wired service is difficult or impossible to get. Now, this does have the potential to change with the throughput speeds and technology that's available with 5G, so I expect to see a lot more local access from wireless in the future, but for now, it's a pretty small part of the market. In our travel example, the most likely use for satellite would be to connect in your in-flight Wi-Fi. As we discussed with Peter, very little of global internet traffic is bouncing up to space and back. Sending things to space is very expensive, even compared to digging trenches and hanging wires, and satellite service has long been the much more expensive option than wired service. However, satellites are still a crucial part of the transport network because they do two things that wires can't do. First, they have the ability to reach moving targets like airplanes and ships. And second, they can get very quickly deployed to very remote or hard to reach locations. So imagine you are a mining company that all of a sudden has to go out to a very remote location. Digging a new trench with a new wire would be very costly and time consuming, whereas turning up a satellite signal could be much, much faster. We are currently in something of a satellite boom driven by companies like Starlink and Kuiper that have been lowering the cost to get these satellites into orbit. So this may change as satellite service becomes more ubiquitous and affordable. Now, let's think about who owns these networks. One of the things I find most fascinating about the global telecom ecosystem is that no one is in charge of it. It's an example of spontaneous, voluntary cooperation across thousands of companies and hundreds of countries. Most of the global internet is owned and operated by private companies. Some of these companies operate in each of the segments of the transport network that I've outlined. Others operate in only one or a handful. So how about local access? Well, some local access networks are operated by the largest telecommunications companies in the world, such as names that you probably know: AT&T, Verizon, NTT, which is the state telecom company in Japan, British Telecom, Orange, which used to be France Telecom, etc. Even for these companies, they are usually only operating local networks in their home countries. So AT&T and Verizon are a local access operator in the United States, but not really in a lot of other countries. Other local networks are provided by hyper-local companies, operating perhaps in a single state or province or even single metro area. Some build networks mainly to sell service to other carriers who need to connect offices, corporate sites, and some are local ISPs or rural telecom companies operating in smaller markets that large companies don't serve because of the economics. Cable companies with coaxial service, DOCSIS like we talked about, are often called MSOs or multiple service operators because they started out selling TV and then moved into broadband. They own many of the local networks and eyeballs in countries that had cable television before broadband came along. Then on to the middle mile. As with local networks, the middle mile may be part of a global carrier's network. Again, particularly in their home country, although much less exclusively than would be the case with local access. And again, like local access networks, there are companies that primarily provide middle mile, connecting eyeball providers to large IXPs and data centers and cloud service providers, etc. Others might also be local access providers. So there's a wide variety of providers in the middle mile, but probably less so than in these other categories. Then terrestrial backbone. As you might imagine, terrestrial backbone providers are often also the larger global or regional telecom companies. However, even in this segment, there are pure play providers that focus on this market in particular. Some carriers specialize specifically in providing internet backbone to other service providers, mostly between major IXP cities. And some of those might operate only between a couple of key cities where they have some reason to be specialized on that route. Then submarine cables. The topic of who owns submarine cables really could be an episode all of its own. So I'll have to summarize a bit more in this category than I did in others. But of course, once again, large regional and global providers are in this market. However, there's a big difference in ownership in that generally carriers don't build their own cables, but join a consortium of many carriers that have a need to cover that particular submarine cable route. So beyond carrier consortiums, cables are sometimes operated by pure play submarine cable providers who mostly exist to build and sell service on submarine routes, often a single route or region. Finally, in the past decade, the big content providers got into the submarine cable game, and many cables are actually just owned and operated by the folks who used a lot of the cables, the likes of Amazon, Google, Meta, and Microsoft. So what is the business model for all of this service? Why do these companies build and maintain this expensive infrastructure? Well, the answer, I hope you would guess, is to make money in almost all cases. There are a few government or institutional networks out there, but the vast majority of these are for-profit companies. Telecom companies build networks to sell them to other telecom companies, cloud providers, content providers, large enterprises, small and medium businesses, and of course, you, the eyeballs. The economics of all of this are complicated and once again would deserve an episode all its own. But the key takeaway for the purpose of this series is that prices vary all around the world based on your geography and also based on which leg of the transport network journey you're on. Another key takeaway on the economics is that at the network level, prices tend to fall due to ongoing increases in supply with new technology and fiber builds constantly influencing the market. Now, this is not so much the case in local access, but again, that is a topic for another time. However, demand for data is always growing as well, which offsets that supply increase. Humans' demand to send bits around the world shows no sign of slowing down. So even though the supply is constantly increasing, the demand is as well, but prices do still tend to constantly go down. Finally, the life cycle of a YouTube video. You might recall from the first episode in this series that to illustrate how the internet works, I thought it would be fun to use a real-world example we are all familiar with. I'm going to relate what we talked about to the life cycle of a YouTube video. Even if you've never uploaded a video to YouTube, you very likely have watched some creator, possibly working from a home studio, which is how I envisioned this example. Once again, our content creator films themselves doing something. Let's say demonstrating how to do a wheelie on a mountain bike, how to draw a dragon, or how to make the perfect soft-boiled egg. Once their edits are done, they upload the video to their YouTube account. The bits of that video leave their house, travel through the wires, either buried or hanging on poles in their neighborhood, until they get to the first aggregation point, that central office, somewhere in their town or very often even in their individual neighborhood. There, the bits leave their ISP's network and onto a regional middle mile provider's network. In this case, maybe one traveling along a railroad line towards the nearest major metropolitan area. Once the packets are in the big city, they go to an IXP. This is probably located in a huge windowless building the size of a massive warehouse, where dozens of carriers interconnect their networks with each other. Just down the street is another massive building owned by Alphabet, or Google, that houses the YouTube servers. Now let's assume we have some pretty popular influencers here. So immediately when their videos are indexed, subscribers are alerted and start streaming the video. Copies of the packets are now going to YouTube servers all around the world, first across these terrestrial links between major IXPs in big cities, then hitting the submarine cable landing stations, traveling across the sea, and doing that whole journey in reverse to get to the fans downloading the video. Well, I hope you understand the transport network a little better now, and make sure you stay tuned next time where we're going to talk about what happens in those big windowless, high security places known as data centers. Until next time. Thanks for listening. TeleGeography Explains the Internet comes from the experts here at TeleGeography. It's edited and produced by Jane Miller, and it's hosted by me, Greg Bryan. To learn more about our data, jump over to telegeography.com, and we'll see you on the internet.